Hi there, Prof here. Welcome to Electronics101. If you haven't watched my previous videos, then I will entreat you to do so, since this is a continuation of the previous ones. I know that most of you are kind of in a hurry to start building some stuff, start putting components together, but then a few experience I've had over the years has shown me that you don't have to rush into electronics. You have to make sure you understand the underlying science, because that is key to becoming a great electronic designer. Electronics is all about science, it's about physics, it's about understanding the basic concept. And if you can't make sense of the basic concept, or if you can't reason in that in the fundamental, then you are going to find it difficult to come up with very cool circuits, or even understand basic circuits when you see them. So my advice is that pay attention to every details and make sure you understand it. A good foundation is very important. Okay, let's get started. In the previous episode, I talked about resistors and their function in circuits. In this episode, I'm going to show you how to read resistor codes. Knowing the resistance alone is not enough in circuit design. Resistors come in different sizes. The size of the resistor contains information about their wattage. Sometimes it's just funny when people's resistor begin to blow up in their circuit, not because they didn't choose the right resistance, but the reason is they failed to choose the right wattage. You can get the same resistor. Let's say you can get a 10 ohm resistor but with different wattages. You can get 1/8 watt, 1/6 watt, 1/4 watt, half watt, 1 watt, 10 watt, etc. So when using resistors, knowing just the resistance you have to use is not enough. You also have to know the wattage, that which is as a result of how much current and how much current is going to pass through it, and how much voltage is going to drop across it. A fixed resistor is a resistor whose resistance is known and it stays the same. The resistance of a fixed resistor is usually stated either by using the color coding scheme or the letter and digit coding scheme. This table shows the interpretation of the resistor color coding scheme. Generally, the scheme is made up of significant figures, multipliers, and tolerance. Some fixed resistors have 4 color bands. There are also 5-band and even 6-band resistors, but the common ones are the 4-band fixed resistors. Now, for a 4-band fixed resistor, as we have here, the first color. Now, looking at this, you realize that it's quite confusing which you should choose as your first color. Now, usually the first color or the first band is very close to the terminal. So if you take this resistor, for instance, this is the first band. If you take this one, this is the first band. If you take that, this is the first band. And usually the tolerance, which is the 4th band, the colors are usually gold, silver, and no color. So it's quite easy to know where to read from. Okay, so if you pick a 4-color band fixed resistor, it is made up of 2 significant figures. So if we take this one, for instance, then the yellow and the violet becomes the first 2 significant figures. The third value becomes what we call the multiplier, and the 4th band or the 4th color is what we call the tolerance. The tolerance of a resistor is the percentage error of the resistance of the resistor. Now, how do we calculate the value of the resistor? By using the color scheme. So to calculate the resistance of a 4-band fixed resistor, what you do is you multiply the first band by 10, then you multiply the second band by 1, and then you add the result of the first band and the second band, then you multiply the result by 10 raised to the power the multiplier. So that is what I've stated in an expression here. So for R4, which stands for the resistance of a 4-band resistor, you multiply the first band, FB stands for first band, by 10, and SB stands for the second band. So when you add this and you multiply the result by 10 raised to the power m, where m here is the value of the multiplier band. Okay, then afterwards you add you append to it the tolerance value. So let's give it a try. If we look at the table here, we have the colors black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, and silver. Now the way I remember this is black brought red oranges yesterday, green blue vines grow well. So that is how I remember these values. Now black has the value 0 as a first band, second band, third band, and even as a multiplier, followed by brown, which is 1, red, in that order. So the maximum is 9, which is white. Okay, so let's try and calculate the resistance of this first resistor here. This is the first band. Take note, this is gold, and you can't have gold as a first band, at least for this case. So we have orange, white, orange. So let's come to the table. In the table, orange is 3. So 3 times 10, which will give us 30, plus white. Now white is 9. And since it's the second band, we multiply it by just 1. So it's just the same 9. So we have 30 plus 9, which is 39. Then the third color, or the third band, is orange. When we come here, orange. Now take note, this is a 4-band resistor, so the third band is the multiplier, not a significant number, and that represents 1K. Is that okay? So in effect, the resistance of this resistor is 39,000 ohms, or 39K. Okay, and the tolerance over here, we have gold, and gold as a tolerance represents 5%. Okay, so the value of this resistance is 39 kilo ohm plus or minus 5%. Now let's look at this one too. We have yellow, violet, black. Now if we go to the table, yellow is 4, so we multiply it by 10, making 14, plus violet is 7, so that gives us 47. Now the third band is black, and because this is a 4-band, the third band is a multiplier, and black as a multiplier is 10 raised to the power 0, which will give us 1. Okay, so we have, in essence, we have 47 ohm resistor. 47 ohm resistor. Now a quick trick is this: any resistor with a black third band is below 100 ohm. Every resistor with the brown third band is below 1K or 1000 ohms. You can do the rest for yourself. Now let's look at this one. So we have red, red, red. Now red as a first band is 2, so times 10 making 20. Red as a second band is 2 plus 20 making 22. Red as a third band here is a multiplier, and that will give us 10 raised to the power 2, which is 100. So in essence, we have 2200 ohm, which we can also call 2.2K. So you can go ahead and try the rest of the resistors. Okay. For a 5-band resistor, there are 3 significant figures or values, and these are the first, second, and third. So if you take this one, we have 1, 2, 3, 4, 5. So this constitutes a 5-band fixed resistor. So this is the first band, second band, third band, fourth band and the fifth band. Now these guys are going to be very tricky, but this I know for sure that this is going to be the first band. Okay, so here we have three significant figures, and in view of that, the first band is multiplied by 100, then you add it to the second band, which is multiplied by 10, then you add it to the third band, then you multiply the sum by 10 raised to the power the multiplier, followed by the tolerance, as we did for the 4 band resistors. Okay, so let's see what will be the value of this resistor now. This color I can't actually see it well, but let's see. I don't know whether it's silver or gold. It looks brown, but wait, okay, we have tolerance for brown, so yeah, that is tolerance. Okay, so let's start. We have brown, black, black. Now when we come to our table, brown is 1, so 1 times 100, which is 100. Then we have black, which is 0, so 0 times 10, which is 0, and the third band 0, so in effect we have 100. Okay, we have 100, and remember here the fourth band is the multiplier, and it's red. Red is 10 raised to the power 2, which is also 100, so we have something like 100, 10,000. Yes, so that gives us 10,000. Okay, 100 times 100, so that gives us 10,000, and the tolerance is brown, so that is plus or minus 1%. Okay, so this resistor is a 10k resistor. Okay, now if you want to find its equivalent color code in the 4 color band system, then 10k is going to be brown, black, orange. Yes, 10k is going to be brown, black, orange, but in the 3 band system, a 10k is brown, black, black, red. Okay, brown, black, black, red, because we have brown here, which is 1 times 100, which is 100. Black times 10, black is 0, which gives us 0, 0. So the sum of these 3 color bands gives us 100. Now this is 2 raised to the power 10 raised to the power 2, which also gives us 100. And if you look at the formula here, we multiply the sum by 10 raised to the power the multiplier. So we have 100 times 100, which gives us 10,000, and tolerance of plus 1, because the tolerance is brown. So this is 10,000 ohm or 10 kilo ohm. Then finally we have the 6 band resistors. That is quite tricky, but if you look at this, we have 1, 2, 3, 4, 5, 6. Okay, and then the 6 band works the same as the 5 band resistors, with the exception that here the seed band actually gives us information about what we call the temperature coefficient of resistance. Okay, temperature coefficient of resistance specifies the maximum change in resistance with change in temperature, and it is measured in parts per millions per degree Celsius, which is ppm per degree Celsius. So that is the unit for temperature coefficient of resistance. Now, to convert from ppm to percentage, all you have to do is to divide the ppm value by 10,000. For example, if we have a resistor with a temperature coefficient of resistance of about 100 ppm per degree Celsius, then it's the same as 0.01% per degree Celsius. The temperature coefficient is only marked on more accurate resistors. For these resistors, those with temperature coefficient of about 100 ppm per degree Celsius are the most popular, and they will work in most reasonable temperature conditions. The others are specially designed for temperature critical applications. Now let's look at how we calculate the resistance of a 6 band resistor. So like I said, the formula, apart from, with the exception of the 6 band, everything is just like the 5 band resistor, with the addition of the temperature information. So if we take this one for instance, we have brown, black, black, brown, green, red. Okay, so if we go to our table, brown is 1 and we multiply it by 100, giving us 100. Black is 0, so we have 0 times 10, which is 0 plus 0, so the 3 significant figures still gives us 100. Then we have brown here. Brown is 1, and in this case it is acting as or serving as a multiplier. Okay, so we have 10 raised to the power 1, which also gives us 10. So 100 times 10, that gives us what? 1000 ohm resistance. Then green here is the tolerance, and if we check green in the tolerance value, that is 0.5 plus or minus 0.5%. Okay, and the last band, which is a 6th band, is, should I say, yeah, it's orange, and orange is 15 ppm per Kelvin. 15 ppm per Kelvin. Okay, so this resistor here is a 1 kilo ohm resistor with a tolerance of 0.5%. Equivalently, on the 4-band resistor scheme, that is going to be brown, black, red. Okay, so you see how the color codes make things a little bit different. But then if you see these 5 bands and 6 bands, usually you get scared because these guys are very familiar and very common. But hey, remember, it is just a simple trick. For the 6 band, the last digit contains information about temperature. Then also we have the letter and digit coding system. Okay, now in this coding system, if we have something like 0.47 ohm, which is usually a fuse resistor, we will write it as R47. 1 ohm becomes 1R0. 4.7 ohm becomes 4R7. So when you see these values, don't get scared. Okay, the meaning is very simple. 100 ohm becomes 100R. 1 kilo ohm becomes 1K0. 1 mega ohm becomes 1 M. And here, to the way we define the tolerance is by using the letters F, G, J, K, and M, where F stands for plus or minus 1%, G stands for plus or minus 2%, K stands for plus or minus 5%, K stands for plus or minus 10%, J plus or minus 5%, and M stands for plus or minus 20%. So whenever you see any of these guys there, please don't be scared to read them. Okay, so over here I have some surface mount resistors, and you can see clearly that this is 4R7, so that tells you that it is what? A 4.7 ohm resistor. This is 0R22, that means it is a 0.22 ohm resistor. This is a 0 ohm resistor, so it could be coded like this or like that. Okay, then we also have this 2, 2, 3, so 22 raised to this 3 is 10 raised to the power 3, so we have 22K. And we also have these guys. Now these are usually used in the SMD environment. You can check on Google for more information. Now when choosing a resistor, you will have to know its wattage too. The way you do that is by calculating how much voltage is expected to drop across it and the current that will flow through it. By using the formula P equals to IV, you can calculate the wattage. Usually, what you do is you choose at least twice the wattage needed. Okay, for instance, if a resistor is expected to drop about 10 volts and allow a current of about 1 amp to pass, then the wattage according to the P equals to IV formula would be 10 watt. So choosing a 20 watt resistor will be the best thing to do. If the size will matter, then try using something like a 15 watt, or at best split it into a number of parallel resistors. We shall look at this again when we get into circuit design, because it is a very, very, very important concept. Basically, there are two types of resistors. We have the linear resistors and non-linear resistors. For non-linear resistors, they do not obey Ohm's law. That is, the current that flows through them does not change according to Ohm's law. We stated Ohm's law in the previous episode. Okay, so for nonlinear resistors, the current that flows through them does not obey Ohm's law. And sometimes these changes could be affected by change in temperature, a change in light intensity, or even an applied voltage. Okay, now examples of these non-linear resistors include what we call the photoresistor or light dependent resistor, LDR for short. Now, for photoresistor, its resistance varies with light intensity. Okay. Now, for a thermistor, its resistance varies with temperature. So that is how it gets its name. Then varistor is a voltage dependent or a voltage dependent resistor. So here its its resistance actually varies according to the voltage across it. And a typical example is a move. Okay, move, you can read about it. So here are some examples. So this is a typical example of a thermistor. That's a varistor, or we call it a move. It is mostly using high circuit protection. Okay, AC circuit protection. You connect them at your input so that when there is any power surge, these guys would automatically deal with the rise in voltage. Linear resistors, on the other hand, obey Ohm's law. Now, there are two types of linear resistors. We have the fixed resistors and the variable resistors. Fixed resistors have fixed resistances, as their name implies, and we have four flavors. We have the carbon composition resistors, wire wound resistors, thin film resistors, and thick film resistors. Now, for the variable resistors, their resistance can actually be changed. Okay, sometimes most of the time they have a knob or a slider or some sort of mechanical way of adjusting their resistance even in circuit. Typical examples include the potentiometer, rheostat, and trimmers. Actually, there is not much difference about these things. There is not much difference between these things, the potentiometer and the rheostat. Usually, from my experience, it is how they look like. So for instance, this will be called the rheostat, this will be called the potentiometer, and this guy here and that are called trimmers. Okay, so I think the difference is more of their form, how they look like. Okay, but basically they all do the same thing. You turn something, you move something to change their resistance. Alright, so that is all for this episode. I hope it helps. Thank you for watching. If you are interested in learning programming with C++, then check my C++ 101 tutorials also on this same channel. Don't forget to like and subscribe to this channel. I am Prof, and this is TechFound.